Good morning, folks. I'm going to get started on time because we've got a fully packed agenda, and hopefully whoever's coming in will just miss some of the boilerplate in the intro. I'm Dave Plonka. I'm remote in Madison, Wisconsin, so I'm 2 hours east of you guys. Good morning. It's one of the few times when you're remote and the time is more convenient than when you're the local. Miria, would you like to introduce yourself?
Yeah, good morning, everybody. My name is Mia Kulewind.
So Miria and I are chairs of the Measurement and Analysis for Protocols Research Group. If you're joining us again, or if this is the first time you're at MAPRG, a hearty welcome to you. I'm going to spin through a couple slides quickly, and we're going to get set. We've got 8 speakers on the agenda today, and hopefully enough time for your questions and comments. The MAPRG is an IETF research group, and we use the same intellectual property right disclosure rules as the IETF. You should have seen those already, but if you want to see what you're bound to by participating, please take a look at the links here in the agenda and follow those links. Note that this is being recorded, both audio and video, and there's stipulations there for if you have the do not phonograph lanyard, but you participate at the mic now and appear that you're giving up, you're agreeing to have us video you. We have a privacy and code of conduct in the IETF and the IRTF. If you have any problems with people's behavior or whatever, you can contact the chairs or you can contact the Ombuds team, which is linked there, and they will be an ambassador on your behalf to help remedy the situation. These are taken very seriously by the organization, so please absolutely do that. If you have any concerns or questions, contact us or them. So the goals of the IRTF are to focus on longer-term research projects in the IETF, so the rules of the way we conduct it are a little bit different. This is not a standards development organization. The rules are a little bit looser. In fact, for instance, MAPRG, this is the 8th year we've been meeting. We started in 2016, so it's quite a long-running effort to link up researchers that measure internet protocols and their operation with the people that develop them. You can find our group's charter at that link. There's a mailing list, of course, if you need to announce things in an ongoing fashion or want to see what's going on with MAPRG and receive future calls, subscribe to that. The slides are up at that link. If you're already seeing me talk, you're already in MeetEcho. You certainly sign into MeetEcho if you're in the room as well, so because we use that as a way to keep attendance for the meetings and get it a properly sized room and a right timed event for the next time we meet. For in-person participants, there's some tips here about how you use MeetEcho Lite and how you can join the queue at the microphone. We are tight on time today, so I'll apologize in advance if we have to cut you off. It'll lean a little more towards giving the presenter the time than people with questions and answers, but I think we can fit it all in if people stay on time. Remote participants, just watch where your audio and video is on if you don't need it to be. Miria prepared this nice list of recent publications from TMA. Give it a look. These are things that presumably she handpicked as particularly interesting to IETF participants. Thanks for preparing that, Miria, and also thanks for putting together almost the entire agenda this time, or probably the entire agenda. I really appreciate it. So here's our agenda for today. I'm not going to go over it item by item. We'll introduce the people as they come along. But it's tight, and let's all work together to keep this on schedule. So the first talk is a short one, and that's going to be Joris. So let's switch to those slides and get Joris up there. Okay.
Good morning, everybody. My name is Joris Herbots. I'm a PhD student over from Hasselt University, and I'm here to do a quick heads-up talk about a paper we presented yesterday at ANRW, in case you already saw it, on HTTP3's extensible prioritization scheme in the wild. Next slide, please.
Dave, you are moving the slides, right?
No. Okay, there we go. HTTP, we have multiple versions. In a nutshell, the biggest difference there is the way resources are being scheduled. The newest versions have multiple resources on the same connection. And if we're talking about multiple resources, we should be talking about priorities, because that's a way to signal the relationship between these resources. Next slide, please. We have the extensible prioritization scheme, which is the latest addition in this field, which is a way to signal these priorities on HTTP 3 and 2. It's the replacement for its predecessor in HTTP 2, which was way too complex. The idea of the extensible prioritization scheme is to be way simpler. However, when we tried it in reality, we saw a lot of chaotic behavior, and it's way more complex than expected. Next slide, please. The way EPS works is with two basic parameters. We have an urgency parameter, which is basically the priority, with the lowest number being the highest priority in practice, and then an incremental flag, which is an indication whether or not resources can share bandwidth. For example, if you have an image, if you share bandwidth with all the images, if you have 10% of an image, you can show it. You can do the same with, for example, JavaScript files. The way we signal these EPS parameters is using HTTP priority headers and the binary frames that are associated with it. Next slide, please. We tested both clients, so browsers and servers, and what we noticed at the browser side is a lot of heterogeneity. So the main browsers, Chrome, Safari, and Firefox, can actually be divided up into 3 distinct categories with different approaches when they apply their heuristics, so their priorities to resources. Even very different incremental behavior with, for example, Chrome applying incremental behavior as we expect, but then Safari applying it on every resource, which makes no sense, and Firefox actually never applying it, which isn't bad, but not good either. Next slide, please. One of the elements that's also important if we talk about extensible prioritization scheme is fetch priority. That's the only way we currently have as developers of web pages to indicate whether or not we want to deviate from the standard priority being applied to a resource. And next slide, please. The thing we noticed in practice is that browsers also have chaotic behavior here. Chrome tends to ignore 50% of these directives given. Firefox doesn't even have support for it, and Safari is quite deterministic in that if you up the priority, it actually ups the priority in practice, and the same for lowering the priority. Next slide, please. So similarly for servers, we did experiments where we checked the support for popular servers. We tested 12 servers based on popularity, going from CDN deployments to off-the-shelf software such as Nginx and Caddy. There's a whole spectrum of results. You can find those back in the paper. Next slide, please. But let's focus on the partial support ones, because those are obviously the most interesting ones to focus on. A good example of chaotic behavior we see here is, for example, with the default scheduling behavior and the interplay with the incremental parameter. We have these two basic parameters, like I said. Not having support for incremental parameter means being stuck on your default scheduling behavior. And we see that happening for Akamai and Google. For Akamai, this is quite fine because they have sequential scheduling by default. But on Google, this is even worse because they have incremental scheduling. And if you look at Chrome, which is using or actively requesting sequential loads, if you then use Chrome to access Google's own servers, they only schedule in an incremental fashion, meaning that we have diametrically opposed approaches to web performance optimization, which once again makes no sense. Next slide, please. So the key point or the thing we saw is that we have a lot of heterogeneity. That's the whole point of the paper. We have unpredictable behavior at the client side, at the browser side, so at browsers and at the server side. And the tools we currently have to streamline this a little bit are quite ineffective. It's even worse in that if you want to optimize for one browser, you could potentially worsen the experience in others, making it a worst case experience pretty much. This is important because priorities impact web performance, and we care a lot about this as users, but also as website maintainers. Next slide, please. This brings us to the recommendations we bring forward. We have a couple more in the paper, but the two key recommendations are: we need full support for EPS by major deployments. We are currently in a chicken and egg problem state where servers are not having full support because clients are not using them, and clients are saying, well, we're not doing it because servers are not implementing it. We need to break this cycle. So we have inconsistent behavior at this point without basic features. We need those basic features, and the whole extensibility part that's in the title of the extensible prioritization scheme is basically out of the window if we don't even have basic support. Similarly for browsers, the clients, we need better manual control through developer APIs. if we want to work around these browser heuristics or even try to look what works best in practice. For example, allow us to change the incremental behavior. We have no ways of changing that, for example, now through the Fetch Priority API. Not only that, but it would also enable more complex web applications, such as video streaming, which certainly might want to make use of this Priority API. Next slide, please. So that's in a nutshell the findings. Feel free to scan this, or you can also find the paper back on the ANRW overview website that was published yesterday. The talk of yesterday is also online, I saw this morning, so feel free to check those. If you want to talk about this, please find me during the breaks, whatever. Thank you very much.
Exactly. So this was just a short heads up. So you see his face. You can watch the talk online, read the paper, talk to him. But we could also take 1 or 2 quick questions if anybody is very curious about it. But it's fine. It's sorry, go backwards. So just please talk to him. Okay, then we can move on. Perfect.
Okay, I hope you can see me. Can you hear me?
Yes, we can see and hear you.
Okay, I cannot see myself. That's distracting. Okay, I guess the slides just go on when I press on it, or do I also have to...
Miria, when Pascal, when he came up, he's not in the list anymore, and I don't see the button to pass control to him. Where does that go now?
I still see him at the last list. He's at the top now.
Oh, okay. Perfect.
Okay,
so okay, so you should have control of your slides.
Yeah, now it works. Perfect. Okay, my name is Pascal Henn, and I will talk a little bit about looking glasses and BGP. So most of us know the internet as some source of news, or for example, video streaming, or as messengers for communicating with friends or colleagues. But we in this group, we know the internet more like a network of networks, autonomous systems, BGP, and so on. So the internet is, as we know, a fairly complex system. And the routing in the internet is based on policies, and those are implemented by BGP. By the way, I can hear myself a little bit. That's kind of distracting.
Yeah, I don't know how to fix that. Sorry.
Okay, let me just do the smart move. Okay, so routing is based on policies and implemented by BGP. Now, what we do is we observe BGP configurations from different autonomous systems through so-called looking glasses. Now, before we can go into this, let's talk a little bit about the background, because I don't know if everybody is familiar with BGP. Now, in the internet, we have so-called autonomous systems, which are networks on their own. And those have border routers, which are used to communicate with the other autonomous systems on the internet. Those connections also host BGP sessions. BGP itself, as said, I will introduce it. We have prefixes in autonomous systems, and those prefixes should be distributed through the whole internet. Now, A, in this example, has the prefix and uses the BGP sessions to introduce this prefix to its neighbors. Those neighbors, they collect or get the prefix knowledge, keep it inside, and also distribute it further to the other neighbors over the BGP sessions that they have themselves. This is continued until the whole internet, in this example, this topology here, knows or has knowledge about this prefix. This is just a simple example, by the way. Usually policies will not share everything with everyone. Now the whole internet or the whole topology knows the prefix. In this internet or in this autonomous systems and this topology, some of the autonomous systems host so-called looking classes. And those looking classes are basically queryable web interfaces, as you can see here, where you can select a type of query, for example, give it an argument, select a router, and so on, submit your query, and you get a certain output. And this output just has, in this example, BGP routes inside. Now, those looking classes in general are rather a fairly sparse resource. Not all of the autonomous systems implement those looking classes or host them. So what we do in this paper or in this work, we collect their outputs for researchers and for operators. Operators might use them for routing purposes and researchers for validation purposes, as an example. Now, how do we do this in general? Those looking classes, as said, are web interfaces, so they have a URL attached to them. And we collected a list of URLs that point to those looking classes. Initially, we had roughly 3,800 of those URLs, but not all of them allow for scraping or allow for automation purposes. So we had to kind of thin them out. We did that by looking, for example, at the robots.txt, which might disallow scraping, and we removed all of the URLs that had robots.txt that disallow scraping from this list. We did the same thing, for example, for just forbidden automation in their policies, or also if there were any captchas or similar things present on this website. In the end, and this is where the sparsity comes in, we only had roughly 155 looking glass URLs, and some of them even stopped working since then. Now, how do we collect the outputs is the next question. Well, we have the list of URLs already, and we have a data set, which we know we will produce, right? We will also have a scraper script. Now, the first thing that we did was we collected manually configurations about those looking glass URLs or about the websites that are hosted there. How does this look like? Well, there's again on the bottom right this interface, and on the top left is an example configuration. So you can see there's a type of query, and those are HTML elements. So we can kind of have XPaths that point to those elements, and we can just interact with them using some backend, which is Playwright in our case. On the configuration side up there, you can see that we map one of those query types to one XPath, and so on. Now, what we just did is we went through all of the different looking classes. There are multiple schemes for them, and even mapped those XPaths to the different elements that we need to interact with. There's also a certain output field that is mostly in a new browser tab that is opened when the query is submitted. There we also just collected the container information of the HTML element and saved it into the configuration as well. With those configurations that we now have, we can run the scraper script. And this scraper basically queries after a same scheme for all of the different looking classes in our list. First of all, we have to select the type of query that we want to have. In our case, this is the BGP route. So the backend just clicks basically on this point. We also collect information about BGP summaries though, but the main focus is on BGP routes. The second step is to enter a prefix, which in our case are the RIS routing beacons. Those are 38 prefixes. All of them have a periodic manner or periodic behavior. And they are basically announced new to the internet in a 4-hour interval, which we can use. Then the next step in our execution is to iterate through all of the different routers that are available to us on this looking class. We iterate through all of the routers on this looking class, and then we just submit the query for each prefix, for each router, for each looking class, which is kind of a lot of queries as well. This generates this output, and this output is also given back to the scraper. As said, we collect one of those snapshots every 4 hours. The output then, as said, comes back to the scraper. This is good. The raw data is also saved to the dataset, so researchers or whoever wants to access this dataset can do with it whatever they want. Another step that we do, though, is to pass this output information as well. As you can see here again, this is the output, and those are multiple BGP routes. As an example, this is one BGP route, and it has multiple different fields in it. So we wrote some regular expressions for each of the different BGP attributes or information that we get from this. For example, this field portrays how long a BGP route is already established, and then we just pass them out for all of the different outputs that there are. There are also different output formats, and we incorporated regular expressions for all of them. All of those outputs are then saved in a CSV file format into the dataset as well. So we have lots of information about all of the different BGP routes that we saw over all of the different queries in the dataset on a 4-hour timestamp, or like on a 4-hour basis. This is not all what we did. We also included some meta information from the looking classes themselves, which might, for example, be, as you can see here, which might be the router name, which can have geolocation information, or it might also be a different autonomous system number from the AS that hosts the looking class. Yeah, the router might be in another autonomous system. All of this information together then builds the dataset, which is also distributed. We can send it to you. Now that the procedure is clear, let's see some statistics about the dataset so far. First, we started the collection on the 26th of January this year, which is coincidentally roughly half a year since the start. And we have even data for or since the 31st of August 2023. This is when I started developing these scripts. Now, we collected a total of 36 million BGP routes, which is even more since I collected those numbers. And the average BGP routes that we get per iteration is roughly 25,000. The maximum that we've seen so far was 35,000 routes in one iteration. And the number of looking classes is 167 in the dataset so far. This is more than the list, as I said before, and that's because of the historical data that we have as well. Some looking classes just stopped working at some point. We also have information about 173 ASs in there, which is because of the routers that might be present in other ASs as well. And we have information about roughly 560 routers in there. Now, what can we do with this dataset as well? So we use this for a study that looks into AS diversity, so diverse policies on BGP. If we look at this autonomous system, for example, which has multiple border routers, there might be BGP configurations in those border routers. For example, for prefix 0, we have a local preference of 100. For prefix 1, a local preference of 90. Now, researchers nowadays assume that ASs are not really diverse, or rather it's hard to not have this assumption in their work. And this is basically saying all of the routers have the same configuration. This is a severe limitation, though, nowadays in research, and this is also well known. It's also acknowledged by most researchers. We can look into this with the dataset itself. So let's say, for example, for this prefix 1 on the lower left corner, we have a local preference of 100. This is just reflected in dataset, so we can just search for this. And that's exactly what we did for different BGP attributes as well. So we did this for the AS paths, for local preferences, and for BGP communities, where we had information for 148 ASs for the AS path attribute in our dataset. Out of these, 55, so roughly 37% were diverse, which is not even too shabby. It's a fairly high number. For the local preferences, we had 142 ASs in total that have information about local preferences in the dataset. And for the AS paths, those were to 36% diverse as well. And for the local preference value itself, it was roughly 40%, which is also a fairly high number. For BGP communities, we expected kind of a lot more because communities can be changed between the different peers that there are. We had 88 ASs in total in the dataset, and only 36, so roughly 41% were diverse in this case. And with that, we already come to the end of the presentation. So we have talked about some background information, some the scraper itself, so how we collect the data set, some statistics, and also about some preliminary results that we also use in our studies. And with that, thank you for your attention. And I'm just going to put them in.
Yeah.
Okay, I should hear you.
Perfect. Thank you so much for the presentation, and also thank you for doing the work creating this data set. That's really great. We would have time for questions.
Wes Hertica, USC ISI. This looks fantastic. How large is the collected data volume, if I may ask?
You mean with file size?
Like how many bytes on your disk did it take to store it all?
At the moment, it's roughly 2 gigabytes for the past one.
That's not too bad.
Yeah, we compressed quite a lot.
Okay, if there are no further questions, we actually move on. But please go and use this data set and bring more results to MAPRG.
Yeah, maybe if you go one slide further, there's also my mail address. Never mind. So for people that are interested, they can also contact me.
Yeah, of course. Perfect.
Yeah,
And maybe you're coming to an IETF meeting in future.
Oh yeah, I want to be there in Dublin, so hopefully.
Okay, perfect. Then let's move on.
all right.
Tommy,
Well,
you're
I was
next.
trying to get there, but I was check his
Yeah,
slides.
it's a lot of slides. Don't worry about it.
Yeah. So we got Tommy Pauly up next. Tommy, let me share your slides here.
He will hand it over to you. That should work, right?
Okay. And then we don't have Tommy as the, let's see. All right, I did the pass slide control, so you should have it now.
Thank you.
Go right ahead.
Hello, everyone. I'm Tommy Pauly from Apple. Sorry, I left my badge in my room. I registered, I promise. Okay, so I'll just quickly be sharing some information that we've gathered, and mainly this is kind of like a pitch for the importance of doing protocol testing in various simulated conditions and how doing some of these simulated measurements on different network conditions can help with the design of certain protocol deployments, and then hopefully also for the rest of the IETF for like as we are designing our protocols themselves before we ship them, making sure that they're going to work in all different types of networks. So just for background, there's a cool tool that we have had for many years on iOS and macOS that if you have done development there, you may be familiar with, which is called Network Link Conditioner. And you can do a quick search on the search engine of your choice and find some information. I think Stuart over here has done some WWDC talks that talk about how to use this tool. So I wanted to highlight some of the ways that it can be used to improve some protocol deployments. So very practically, about a year ago, we had a particular setup where we're trying to be using some new HTTP3 based forward proxies. So if you follow kind of the work on MASC, et cetera, these are MASC style proxies, although in these cases, sometimes what we're getting to is just normal TCP upstream hosts, but connecting to a proxy over QUIC. And the intent for this project was to be using these proxies to accelerate connection setup time to help improve the time that apps take to launch when they need to reach out to a bunch of different resources, and otherwise we'll be doing many, many different connections. So we have a particular app we were looking at here that previously would be opening up many different HTTP2 connections and fetching various resources, and there was a lot of handshake times going on there. And if you are on a slow network, that could really add up and end up slowing down the app launch. So we had the theory that, yeah, let's put this over kind of one tunnel over QUIC, and that should improve things. So here's a rough diagram of the setup. So we have a client application, and these orange lines on top and bottom represent kind of the fallback direct case that they could go. It's more than two targets actually, but this is just kind of an example to show the different cases. And in the new protocol setup that we were trying to test, we would have a connection using HTTP3, a single connection to a proxy, which would then have separate streams inside of it that would do the end-to-end HTTP2 connections. And so we wanted to see, what are all the ways we can eke out the performance of setup to that proxy, and by doing tricks like having really aggressive DNS caching or having zero round trip establishment using session tickets, et cetera, and then being able to reuse this pipe for all the connections. So some of the benefits that we were expecting to get, we would have cached DNS answers to save DNS round trips all the time. We would be able to do zero RTT to that relay, so we would essentially eliminate all of the TCP handshake times that we would otherwise have. But then also, QUIC on this proxy, we were able to do a lot of tuning on it, and we wanted to say, based on the placement of this particular relay server, what can we do about adopting BBR or other tunings for congestion control and other things to make sure that we're going to have a good experience across all the different networks. And so a key part of this setup and making sure we were going to deploy something that was useful is to make sure that this is going to perform well in all different types of networks. Because the point of this is, the app launch when you were on a very fast network with low latency, it was always fine. It was not a problem. But it was the outlier cases. It was the P90 cases and above that could get pretty slow. And so we needed to figure out what are the right profiles to evaluate. Just some of the tips I want to share here that we learned when you're looking at something like this network link conditioner. I think it's easy, and there are even some examples built into the OS of like, oh, really, really high loss. Oftentimes that's not very realistic. It's good to try to understand what are the realistic ranges of loss that you would see. It's going to be probably 3% or below, even in the worst cases. Delay and how much you're cranking up delay for both upstream and downstream. Potentially trying to imitate what may happen if queues are building in the network. That's going to be one of the most impactful variables for what you're choosing here. And we found that it was really important to test with at least 3 different profiles for how networks look. Because as I'll show, just testing in some forms of impairment, even if you're saying, oh, this is a bad network, you will be able to hide problems that will arise on other types of impaired networks. So here are 3 example profiles that we used. These are just roughly the tunings here. Now they were trying to imitate some sample measurements, and the names here are not really quite right or representative. But we essentially had one like here's a cable-like network that may be something that someone sees that's not a great connectivity. Here's a much slower DSL network, but something without too much delay. And then we had a sample of like, this is representative, at least some experience we've seen with certain cellular networks in India to say like, okay, what are some different outliers? Now, of course, these are not going to be representative of all the actual networks. We understand there's a lot of diversity, but the point is to get a broad range of delays and bandwidth properties and loss properties here. So as an example, so this is a CDF where we show the kind of overall app launch time for the 2 different paths of using this proxy and not using the proxy. And so this is the overall amount of time it takes to do kind of all of the networking connections and little file downloads that you need to do to be able to like display a UI. And this is kind of in an earlier test that we had done with more naive implementation, not a lot of congestion control tuning, without 0 round trip establishment turned on. And on the DSL lake profile, it actually looked pretty good. It was about the same at the very fast, kind of lucky examples. And then from around P70, they started to diverge, and the proxied case did better. And it's like, great, we're getting an advantage from reusing this connection, from having quick there. So great. But then when you look at the exact same implementation running on that in DSL profile, it had the exact opposite behavior, and we were actually making things worse. So that's why it's very important to be able to test on these different cases. Then later on, we used these and kept repeating the experiments to do different tunings for how the congestion control worked, how aggressively we would be able to have 0 round trip reestablishment. And we were able to get to the point where we were consistently winning across all the different profiles. So then how does this translate into the real world? So this doesn't have those exact same 3 profile breakdowns, but we do have the relayed and direct versions that we can collect from the real world live on data for both like US Wi-Fi networks and NDSL networks as just kind of 2 data points that somewhat map to those simulated environments. And we do see kind of a consistent win. If you look at some of the P90 numbers, when we are doing those relay numbers, like in some of the worst cases, we're like twice as fast, and that matches up to the same numbers we were seeing in the simulated environments. So it's definitely a very effective tool. So the main takeaways that I just want to kind of share and start a conversation about, first, I think it's important that as both in doing deployments, but as we're talking about new ways to put protocols together or new ways to design protocols, that we, during the process of doing that design, we're testing with simulated conditions to see, are the protocols we're designing going to work well in all the different networks that people are going to be living on around the world. And then also potentially as a request to this group and measurement community, it'd be really interesting to have more collaborative efforts to share what are some of the settings and profiles that could be feeding into these types of simulated tests to make sure we have good representative examples of real world conditions that people are seeing all around the world, to make sure that as people at, I don't know, hackathons or whatever, we could figure out ways to say, test out your protocol in these different environments and make sure that you're not missing something that will impact users later on. That's it.
Yeah, thanks, Tommy. So yeah, I guess it's actually important for this community to look at the protocols we develop or the IETF develops and make sure they work everywhere in the world. Yeah, Matt.
How much work did you do to compare the simulations to real measurements?
So I had not done all of the work on kind of like how the numbers were initially chosen. I think there was kind of like that initial input of like, let's get a lot of measurements from certain areas a couple of years ago to build the profiles. And then it was more that after the fact, we just compared the numbers we were getting broadly from the field and said, yeah, like these look like they're roughly the same as what we had.
So you didn't depend on the simulations actually matching reality. You were just testing corner cases, for instance.
Exactly. We're trying, I think, and that's the point. Like, you don't need to have every single network represented. You just need to explore the space to make sure that you don't have a blind spot.
Yes, I strongly encourage that attitude.
Lorenzo Colletti. Not super related, perhaps, but one of the main issues that we encounter when we do these sort of common communication channels like proxies or VPNs is that when you're using UDP, session timeouts are really short on some networks. And what that means is if you put all traffic on these proxied connections, including things like hang and gets and notification channels, right? So what that means is we can never get rid of TCP.
Oh yeah.
Right. So it would be nice to know if first of all, if these simulated environments could like simulate that, but also it'd be nice to know if we have some sort of data or some common data around how low those timeouts are in various parts of the internet, and to see if we could sort of actually change that. Because just keeping TCP around forever and like not being able to do this for important communications means that you can't just use this for everything, and you need to know as an app, oh no, this is a long-lived connection, so I must send it out of the proxy, right? So and then if the proxy is a security functionality, then you basically say, well, I can put the push channel outside the proxy because it needs to use TCP, and security-wise, that's fine because it's already encrypted. And you end up making these sort of judgments that are sort of not great. So I'm just saying maybe it would be nice to sort of either at least collect data or maybe simulate these timeouts as well.
Yeah, it's a good point. Yeah, totally agreed with everything you said.
Stuart Cheshire, Apple. Thank you for presenting this, Tommy. I'll quickly add a bit of background that I think might be interesting to people. Going back more than 10 years now, when we launched the original Apple TV, the big slab one, all the software was developed with engineers with the thing on their desk plugged into wired Ethernet. And because of the secrecy around Apple products, nobody took them home. And when it was ready to ship, they took them home and connected it to Wi-Fi, and it didn't work at all. I mean, I don't mean the performance was bad. Like it couldn't load videos. It just didn't work. And that's why the product was late shipping, and Steve Jobs was not happy that he announced it, and then we found it didn't work. So DummyNet existed as a command line option, but really none of the engineers knew about it. And that was the driver. That specific event was what drove us to put the GUI into Xcode to really try to make this more accessible to application programmers who are not networking experts. So thank you for raising the awareness here, because the scenarios modeled by Network Link Conditioner may be fairly simplistic. It's not like running all the traffic through an NS3 simulation. But if all you do is test plugged into wired gigabit Ethernet, or you just test in your office where you've got great 5G coverage, you're in for a world of unhappy customers when you ship it. So it's so important to do this.
Hi, it's Chris Seal. Firstly, really good to see this work. Thank you. Just a little thing, which I'm sure you know already, but you just refer to cell technology, but I would say that the characteristics of 3G versus 4G and let's say between 4G and 5G are dramatically different. So if we're going to model it, can we kind of separate them out into their technologies?
Again, like this is a label I put there that is highly reductive and inaccurate.
Sure. I'll just, thank you.
I didn't want to call anything out more specifically.
Hello, Kohei Ueno, Google. So I have a question about how the packet loss is simulated here. Like, so do we roll the dice on every packet, or do we consider temporal locality on the packet loss happening?
Didn't quite follow.
So
I don't remember the details for the DummyNet implementation there, but I think that's a great thing to discuss and get into the details of.
Thank you.
Thank you. All right.
Okay, thanks, Tommy. And we move on.
Yeah, thanks, Tommy. Jamo is up next. I'm going to share their slides and pass control.
Right. Can you hear me?
Yes, and great that you're here. So this talk we were supposed to have last time.
Oh, yeah, sorry.
No worries. We had enough other talks last time, so great to have you this time here.
Thank you. I guess I'll get started. Hello, everyone. My name is Jamal Liu. I'm from the University of California, Santa Barbara. This work is done in collaboration with ViSat, which is one of the leading geosatellite provider. The talk is about our paper published in PAM, Watching Stars in Pixels, the interplay of traffic shaping and YouTube streaming QE over geosatellite networks.
Are you still logged in, Jamo?
Yes, I'm logged in, but I cannot really go to the next slide.
Yeah, I have to pass it to you. I didn't see you there.
Oh, okay, there we go.
All right, you should have it now. Thanks.
Okay, yeah, it works now. Yeah, so just a bit of background of why geostationary satellites, right? So, it's actually a very critical part of delivering internet access to the entire world. As we know, there's a lot of very challenging terrains, very challenging environments in this world where laying fibers to those places just become very impractical, expensive, and if not possible, right? So one of the most attractive things about geostationary satellite is that you could actually provide internet coverage for the entire planet with just a few satellites. So as you can see in the top right figure, from ViSat, we essentially provide the coverage for the entire planet, just a few. And as you can imagine, these satellites are actually very far from Earth because the coverage of each satellite is pretty big. As a result, your data must go through a much longer distance than your traditional fiber network. And inevitably, this leads to a pretty long propagation delay in a range of 600 milliseconds in comparison to your everyday, fiber optics of maybe 10 millisecond, 100 millisecond delay. And as you know, like these long delays inevitably lead to a lot of problems at the network level. For example, like the congestion window growth could be slowed down because of the super long feedback loop. So there's a lot of additional components that we introduce, such as proxies, to really mitigate the impacts of these. On top of that, this makes the system really complex and really different from what we see every day. On top of that, for every one satellite, they provide a relatively fixed amount of resource, which is shared amongst many users. And similar to a lot of other wireless ISPs or mobile ISPs, users usually have high priority data usage every month. And once you go over the data usage, then essentially your network becomes slower. So nowadays, when you watch a video, there's different resolutions. A user might innocently watch a very high resolution, even though maybe he doesn't know that uses a lot of data, and then he will just quickly deplete his data, and that makes the customer really happy about it. And one of the practice or the effort trying to do that, trying to prevent this happening, is using shaping, so which is also very common amongst many mobile and satellite ISPs. So these are opt-in shapings by users. The idea or the traditional wisdom is that if we shape our network to a rate that is well above what we want them to watch, for example, for 80p videos, then chances are the user will be happy, watch that resolution and don't use a lot of data. And there's a lot of work actually on understanding the quality of experience, or QoE, versus the bandwidth profile or shaping. But those work are usually done in the settings of terrestrial network. So we want to focus on the geosatellite instead, and we choose YouTube because YouTube gives us the most market share in terms of not most market share, but a very big market share in terms of video watching. So all in all, our research objective is then becomes to analyze the YouTube QoE of geosatellite networks, and in the production Viasat geosatellite networks. So there are three things we have to do. The first thing was collect the YouTube QoE, and as well as the quality of service data from the network. And then we analyze the collected QoE, and we're trying to see this collected QoE is actually below or above our expectation. And if there's any, below expectation QoE, then we're trying to really correlate the QS data to figure out why this is the case. Why is our QoE subpar? Right. So before we jump into the results, I just want to give you a little overview of the network. As you can see, it's a very complex part, but I'll just talk about what's truly relevant. So essentially, we have a laptop at UCSB that's connected to the production Viasat network. Essentially, as I mentioned, the geosatellite network uses TCP proxies that breaks the connection apart into three different parts, namely C1, C2, and C3. C1 is the link between the YouTube server and the TCP proxy server. So this one is mostly fiber and it's pretty low latency, as you can imagine, and the traffic shaper is also here. And between the proxy, the server, and the user proxy, here's the satellite link. And in this link, you usually have 600 milliseconds. And lastly, it's between the proxy between the user modem and the user. So as you know, these are TCP proxies, but Google or YouTube actually uses QUIC as their default mechanism at transport layer. So in that case, these TCP proxies essentially don't work, and they just simply forward the traffic, right? And I also want to mention that the shaping rate we investigated is 900 kbps because that's the very similar rate are used by other mobile and satellite ISPs, and there's a reference from the wiki paper. And also, I want to mention BBRV3 is used at a time when we did the experiment for the congestion control. Yeah, so let's quickly talk about the data set that we collected and the methodologies. So essentially, we stream 13 different videos from 16 different categories. So this gives us a total of 208 distinct videos. We stream each video 5 times with QUIC and 5 times with TCP. And then we collect the YouTube stats for nerds as our QoE metric. So an example is the top right. Basically, the focus is the resolution as well as the rebuffering events that happen during the streams. And also we collect the HTTP performance log for each video chunks and audio chunks. So an example is the bottom right. Essentially, these are the, if you go to developer tools and you go to network tab, and this is what you see. Yeah, so let's set our expectation first for our performance, right? Since we shape at 900 kbps, we want to understand or look at what is the video playback, what is the video bit rate of the videos we've selected. So here, this is given by the graph on the left. We can see that at 360p, 900 kbps is well above the video bit rate. And even at 480p, 900 kbps is above most of the majority of the videos we selected. So this kind of leads us to the expectation that we should be able to watch or stream these videos at maybe a bit more than 360p with minimal amount of rebuffering events if the adaptive bitrate algorithm works pretty well. But is that the case, right? So we found out that actually that's not the case. So 30% of both TCP and quick sessions suffer at least one rebuffering event. And the average resolution is only 404 pixels for TCP and 360 pixels for quick. As you can see on the figure on the right, quick has a lot of sessions that has really low quality, and this is not very good. So even though we can see from here that TCP performs a bit better than quick, but our understanding is that both TCP and quick actually fall below our expectations, and we are really trying to figure out why this is the case and how we can improve on it. So yeah, so we firstly have to model the video transmission mechanism. So similar to previous work, we also observe that the video and audio chunks are transmitted in sequence, like the figure on the left. And in this figure, we essentially break the period down into 3 different parts, right? The first part is the time to first byte. Essentially, is between when the request is initiated to when the request is when the first byte of the data is received. And then you have the transmission period, where where the transmission takes place, the data comes in. But because of the sequence, so it kind of forms a sort of a pipeline. We can also define the period between the end of the transmission from the previous chunk to the start of the transmission of the next chunk. So this is what we call the idle period or idle time. So during this time, there's literally no data being transmitted, and essentially just waiting for the data to come in. In today's network, the idle time is usually pretty small, like in the range of 10 milliseconds, because use fiber and stuff. That's very quick. But in our case, we cannot really have negligible idle time because we use a relatively long propagation delay link of 600 milliseconds. So let's start with the easier part for the analysis, which is during the transmission period. So in this case, we're just trying to understand, when we do transmissions, are we transmitting at the maximum capacity of the link, right? So what we found is on the figure on the right, what we found is that TCP is actually able to saturate the link at around 900 kbps, which is shown by the black vertical line here. Whereas quick actually varies well below the 900 kbps. That means quick is not able to saturate the link during transmission, and the median throughput is only 630 kbps. So this kind of suggests that maybe the BBRV3 has maybe some problems with this long latency scenario. Is something that's worth investigation. And next, we want to understand, okay, how does the idle period really impact our transmission? So in a long latency scenarios, you would really want to minimize the amount of time you spend idling or waiting, and maximize the amount of time you spend actually transmitting. So when we compute the idle time, here's the PDF, and we found that the idle time actually clusters around 600 milliseconds, which is the propagation delay. This kind of suggests that the adaptive bitrate algorithm is not able to really take the propagation delay into account, and so it didn't really take that into consideration, and this inevitably has a much bigger impact for smaller video chunks or smaller audio chunks, because you spend most of the time waiting instead of doing transmissions. So you can see that on the right here. You can see there indeed the chunk size is correlated. to the achieved throughput, and essentially you achieve a plateau as you increase the chunk size. And what makes the problem worse is that YouTube tends to request smaller chunks when the bandwidth is low, and this obviously forms a vicious cycle because you'd have lower bandwidth, smaller chunks, and leads to even lower bandwidth, and this is not ideal in that scenario. So just to wrap things up, actually, we from our analysis, we found that performing traffic shaping to obtain a desired video bit rate is actually quite tricky in geo-satellite networks, and we found that the achieved throughput for TCP and QUIC are only 580 kilobits and 470 kilobits respectively, and this is very far from our targeted or desired 900 kbps. Because of this findings, Viasat has discontinued the support for the low bandwidth data saving options in the US business and residential markets. And lastly, as we kind of encourage content providers, application and product designers to really consider like a wide variety of network types and characteristics in the product to avoid such performance anomalies. Yeah, that will be at the end of it. Yeah.
Thank you so much. We do already have questions.
Yeah.
Ha, I have solved the problem. Lorenzo Coliti, thanks for presenting this. This is very interesting. I have a similar long fat network for reasons I won't go into here. And I've looked at some of sort of the main streaming platforms. One thing that I saw that you didn't see here, I think it was Netflix, was it doesn't just do this chunking, it actually closes and reestablishes new TCP connections. Mm-hmm. And so each chunk actually suffers from slow start, right? And so it really takes a while. And you can literally see if things go well, it starts to kicks into this higher bandwidth mode. And when it tries to drive the network harder, it will actually go faster for a while. And then it'll experience some loss. It'll go, I was like, oh, this network is slower. Let me throttle down. So I think definitely it's not just, I mean, YouTube probably reuses TCP connections because it's a streaming thing. So it can't really close them. But even if you close them, in some sense, you get even worse. Now, I don't know how to solve this, right? Obviously, I guess from a satellite perspective, you could like say like, oh, we'll block QUIC, and everyone's like, oh, you're really evil. Yeah. And then you like basically implement TCP performance enhancing proxies, and they're like, oh, these middle boxes are. But you're in a tough spot, right? So I don't know how to solve this, but it's definitely very interesting, and I think presenting it may be a first step to getting people to sort of understand how, that the quality of experience is not great. Thank you.
I agree. Thank you.
Hello, Gary Fairhurst. Thanks ever so much for the talk. I mean, it's really good to see things analysed at different levels and try and unpick what's going on. That was really useful. There's stuff in TSVWG on a careful resume draft for QUIC, which might help considerably with restarting QUIC over high BDP paths. So that might be something to look at. I don't know if you looked at it.
No, I personally have not looked at that, but I'll definitely like something to look at.
Love to follow up on that one. And also maybe the SCOM Pro buff this time. So it's so timely to see this talk. Thank you ever so much for being here.
Thank you.
Hello, this is Jay Chung. I actually worked on this project with Gemma. Just want to actually make a comment that we actually know that, especially when the protocol, either TCP or QUIC starts, the slow start is one of the enemy to, improve the performance, for almost all, networking in a long RTT high BDP network. So what we're trying to do is, we're trying to actually optimize the slow start performance, and that's basically, the most bang for the buck, so that's the research direction that we are actually heading into. We have on the talk in CCWG on this, so if you're interested, thank you.
Yeah, thank you. Can you join the queue next time?
Ben Schwartz, Meta. So I heard a lot of comments about high bandwidth delay product being a source of the issue here, but actually the solution to this was to increase the bandwidth delay product by, in this case, removing the bandwidth limiter, right? So actually the system performs very well at high bandwidth delay product. And the thing that makes it perform badly is the traffic shaper. So I think the interesting question here is, what is the traffic shaper actually doing precisely? Because if all it's doing is simulating a lower bandwidth network accurately, then maybe everything would work better. The reason I mention that is that, as the proponents of the scone probe BOF have been pointing out, the behavior of adaptive bitrate video on networks that use traffic policers to try to reduce video bandwidth is extra specially terrible and weird. And so I would just suggest that you pay very, very careful attention to the precise behavior of your traffic shaping systems here. Those details matter a lot and could explain the anomalies you're seeing.
Yeah, just a quick comment on that. So it's a shaper, it's not a policer in the sense that it doesn't drop the packets if it's above the rate. So yeah, so maybe that's.
Yeah, so I mean, it's great that like shapers that are like non-policing shapers are generally, I think, less prone to these kind of anomalies. But even so, I think I would just want to be very careful about whether you're accurately reproducing the behavior of an ordinary network or not.
Thanks, Ben. Let's take Matt next, and we'll close the queue on this one. We're running in pretty close on time, so go ahead, Matt.
10 years ago, I knew the people who designed some of these algorithms, and there's always a lot of complexity about, I'll say, anticipating content. We'll put it that way. And one of the things that an experiment that might be useful to do is we run these on a network that you can completely control all the parameters, so a synthetic delay on a terrestrial network, and see if there is delays where behavior changes. Because there might be timers in the design of the serving that either should be adaptive or not, or something like that, and provide insight of that source to the implementers, because YouTube would like YouTube to work everywhere. And constructive feedback might actually be useful.
Sure.
All right. Thanks so much, Damo. I'm going to switch over to Amanda now. And Amanda, I just passed control to you, so you should be able to switch your slides. I think we have you on the agenda for 15 minutes.
Mm-hmm. Yeah. Does everyone hear me okay?
Yes,
we do.
Great. Cool. I'll just get started then. So my name is Amanda. I'm a PhD student at Georgia Tech, and today I'm going to be presenting to you a first look at NAT64 deployment in the wild. This was a collaboration between myself, my two advisors at Georgia Tech, as well as Oliver Gosser at the Max Planck Institute for Informatics. And this is also work that appeared at the Passive and Active Measurement Conference last March. Okay, so before diving into this work, just going to give you some brief background to kind of build up our motivation. So I'm guessing most of you have heard about IPv6 adoption, and IPv6 adoption has increased a lot in the past 15 years, and Google has reported that almost 45% of the traffic that it receives is IPv6. And this is great for a lot of reasons, but it does present some problems. So when we looked at popular domain top lists, such as Cisco Umbrella, we saw that about 70% of these domains are actually only available over IPv4. And so if any of these clients are not dual stack, meaning they are IPv6 only, how do they access all of this content over IPv4? Luckily, there is a solution, and it has existed since the conception of IPv6, and it's to use transition mechanisms to bridge this gap. And today, I'm going to be talking about one of these transition mechanisms called NAT64. I'm just going to briefly go through how exactly this works so you can understand each component. An IPv6-only client will begin by trying to resolve a domain to a DNS64 resolver. However, if this DNS64 resolver realizes that there is no quad A record, meaning this domain only has an A record over IPv4, it's not just going to return this to the client. Instead, it's going to create a synthetic quad A record and give that to the client. And the address on this synthetic record can be from the special use prefix that is commonly used for this purpose, as we'll see, or it can be from some other globally unique IPv6 space or some private space. But regardless, one important bit here is that the last 32 bits of this address are going to embed the 32 bits from the IPv4 address. And once the IPv6 client has this record, it can use this address to then access the NAT64 gateway, and the NAT64 gateway will then actually take care of the translation between v6 to v4 and essentially allow the client to access content from this domain. And in this work, we sought to characterize and measure NAT64 deployments. And what our methodology is really centered around is requesting a quad A record from a resolver, and it's for a domain that we know is only IPv4. That way, if we get a record back, we know that this is potentially using DNS64. In this work, we wanted to understand NAT64 from a few different perspectives. One is just deployment. So is NAT64 prevalent and can we measure it? Next is, if we can, how are they configured? So for example, what kind of address space are they using? And last is security. So if we find these NAT64 gateways, are they publicly accessible? Following that, we also sought to use a few different perspectives in our measurement methodology. The first is, as I said, we use DNS resolvers. And so we look at IPv6 resolvers from the IPv6 hit list and IPv4 resolvers from the census data set. Next is we also want to understand the client perspective. So we look on the RIPE Atlas platform and we determine whether or not a probe is using NAT64. Lastly, we want to understand the server perspective. So if a client is accessing a server using NAT64, what does that look like and what can we learn from it? So we actually set up a domain and we only create an A record for this domain, and we use RIPE Atlas probes to send various measurements towards it. Okay, let's just dive into the results. Before actually talking about what we find, I want to explain these plots to you a little bit. So first, we categorize the responses from DNS64 resolvers into what kind of addressing they're using. So either the public IPv6 space, the NAT64 special use prefix that I showed on previous slides, or some other kind of private space. Next, we measured, or we tried to resolve various domains to these resolvers. And one thing I want to note here is at the time of these measurements, these domains only had A records, so they were IPv4 only. But I know that since the time of the measurement, at least one of these now has a quad A record. But then we also looked at how consistent those results are over all of our domain measurements. So how many resolvers are actually responding in the same way for all of these domains. So I'm just going to dive into some of the maybe more obvious results that you can see from here. First is that using the NAT64 special use prefix for addressing is the most common. So this kind of gives us a clue to the most common configurations for these deployments. But I also want to point out something else that you may have noticed if you notice the y-axes of these plots, and it's that we're really not talking about a lot of resolvers here. So we measured almost 2 million IPv4 resolvers. We measured almost 300,000 IPv6 resolvers, and in both cases, way less than 1% indicated that they're using DNS64. And what we can conclude from this is that DNS64 is not deployed widely across public resolvers. And I want to be very careful with how to phrase this and emphasize public, because with this vantage point for our measurements, we don't have vantage into private resolvers. But from what we did find, we can do just a little bit of analysis on what kinds of networks they're in. So you can see in both v4 and v6, China Telecom is in both lists. And we also see a lot of different kinds of network service providers in these lists. And so from this, what we can conclude is that public DNS64 resolvers are concentrated in mobile and network service providers, as well as some Chinese networks. I want to point out one last thing just about these results that you also may have noticed if you look at these plots closely, and it's that there are some inconsistencies in the results that we're seeing, depending on what domain we tried to resolve. And what I'm trying to point out here is just one particular outlier for a domain. And when we look deeper into these results, we found that a lot of this spike is mainly due to resolvers in China Education Network that respond to requests for this domain, but no other domains. And we can't actually exactly pinpoint exactly what's happening here, but this is something that's important to keep in mind, I think, for future measurement work that involves resolvers. So let's dive into what we found when we looked at clients. So how many RIPE Atlas probes are actually using NAT64 for their connectivity? Really similarly to resolvers, we found that the answer is not many. We measured over 5,000 probes, and only 0.7% actually indicated they were using NAT64. Similarly to resolvers, again, the address type distribution is similar, with the special use prefix being the most popular, followed by public addresses. We then wanted to see if these probes are concentrated in any particular network. And the answer is not really, although we are talking about a very small amount of probes in general. But we did find just under 25% are either in Deutsche Telekom or Melchiwan, which are ISPs. And what we could conclude here is that clients are not largely using NAT64. However, I think we should all take this result with a grain of salt because the RIPE Atlas platform, although it's a really great resource, it is not guaranteed to be an accurate representation of clients on the internet at large. And so whether or not this result actually represents the internet in its entirety, we can't be sure about just from this measurement alone. Okay, we're going into the last result that I wanted to talk about here, and it's on the security of these gateways. So are these gateways publicly accessible? But before diving into the results, I'll explain a little bit of our methodology. So we, as you may remember, we're issuing requests to DNS64 resolvers. But if the synthetic quad A records that came back to us had public IPv6 addresses on them, meaning they're not from some private space, we actually did a follow-up measurement where we issued HTTP and HTTPS requests to that NAT64 gateway for the domain and the IP that was on that quad A record. And then once we got those responses back, we compared them to control responses. And what I mean by that is these are HTTP and HTTPS responses we just made to that domain as if we were just trying to regularly access the content. And then we compared them and basically determined whether or not we were accessing the content as intended. So what did we find? Well, at large, these gateways are not publicly accessible. And so in HTTP, we found anywhere from 1 to 26% of our responses were quote unquote correct. And in HTTPS, we found anywhere from 0.6 to 15.6 were correct. Some of the responses that we got specifically in the certificates were certificates for anything from hosting provider domains, park domains, or domains that had nothing to do with our measurements, such as Netflix.com. And so from this, we can conclude that NAT64 gateways on public IPs are not largely accessible publicly, which is actually a good thing for security, because if one of these was open unintentionally, this could be a problem. All right, so let's just summarize what we covered in this talk. We saw that DNS64 resolvers are not deployed publicly at large, and we also saw a lot of variance in our resolver measurements. Next, we saw that clients on the RIPE Atlas platform are largely not using NAT64, although this may not necessarily be representative of the internet. Lastly, we saw that most NAT64 gateways are not publicly accessible, and something that we didn't get to touch on in this talk is that when we actually looked at the embeddings, so those last 32 bits, we did see that most of these were embedding the A records correctly. I also I just wanted to take some time. I see that I do have a number of questions already, which is great. But clearly in this work, we're limited a lot by our vantage points for our measurement. And so if anyone has experience or your network is using NAT64, I would love to learn about your experiences with it. And we also generally welcome any input on our methodology and findings. And you can also reach me at the email address on the screen. Thanks for listening.
Thanks. Yeah, we go ahead with questions.
Hi, Jan Linkova, someone who deployed V6 only network in the large enterprise. So a few comments. First of all, DNS64 is not strictly speaking required for V6 only clients using NAT64. You can, if clients using CLAT, you can provide them the NAT64 prefix via other means, such as information and router advertisement, right? So it should be completely decoupled things. Secondly, you measured public resolvers. Obviously, for things to work correctly, you need completely different resolver to be DNS64. For example, Google public DNS. It's one thing, and Google public DNS64 is completely different VIPs, right? So I think it's actually broken configuration if public resolver provides like DNS64 answer in general, because it might cause some delays for the client, right? So you need to be like, I would say, slightly more careful. And also RIPE Atlas probe would not probably represent much, because I believe, like Robert can correct me, they're mostly sitting at home networks, right? While I would expect like DNS6, like NAT64 devices being mostly deployed in other environments. And my last comment, I'm not sure you said that you see clients using NAT64. How do you know if they're using NAT64? Because using DNS64 and being behind NAT64, it's actually different things. You strictly speaking cannot distinguish, right? In my network, NAT44 and NAT64 is the same device doing the same pool. So there's no way you can tell unless you know your client is V6 only.
Yeah. Thank you so much for all the comments. Just to answer your question about the RIPE Atlas probes, the way that we determined whether or not it was using, I guess, DNS64, using your correction, we actually attempted to resolve, we requested a quad A record for some of those domains that we knew only had an A record, and then we were actually able to look at the responses to see what the response was.
Yes, so it means your client using DNS64.
Yes.
It does not mean it's using NAT64 actually to reach the destination, strictly speaking, right? It does not guarantee
Yes. Yes, definitely.
I'm Stuart Cheshire from Apple. We've got a bunch of people in the queue, so I'll try to make this short. My comments are very similar to Jen's. I think when studying this, be really careful to separate NAT64 from DNS64, because NAT64 is broadly a good idea and DNS64 is broadly not. When this was first created, I think more than 10 years ago, there was some notion that you put in a NAT64 gateway and then you put in a DNS64 hack that lies to the clients, and that magically makes it all work. I understand that seemed logical at the time, but the reality is we only have a handful of clients we really care about. There's Mac and Windows and Linux and Android and iPhone and a few others. But compared to the millions of websites in the world and thousands of service providers and thousands of DNS resolvers, there aren't that many clients. And the reality turned out that it's much easier and more secure to have the client do the synthesis locally. Take a look at RFC 8880, 8880 that talks about that, because DNS64 breaks DNS security, and security is important. If the client synthesizes locally, it can actually validate the DNS answers and synthesize for itself. Using DNS64 is also a problem for the reason Jen said, that if you're on some network that uses NAT64, but you choose to set quad 8 as your resolver, the whole tying of NAT64 to DNS64 assumes both services are run by the same entity that knows what prefix it's using. So there's a whole list here. Clients can discover the synthesis prefix using router advertisement options. There's a bunch of ways the client can do this. And my last comment, that there's a home wireless network technology called Thread that is a low-power wireless mesh for IPv6, and it only supports IPv6. So every Thread device is a v6-only device, and Thread border routers are all required to provide NAT64 and not DNS64. All Thread nodes that want to access a v4 host are required to do their own local synthesis for exactly this reason, so that DNSSEC works. So this is a good study. What I'm saying is be really careful to separate NAT64 and DNS64 because they have quite different properties and quite different deployments.
Hi, Ben Schwartz. I'm pretty sure that there are hundreds of millions of people in the world whose internet connectivity depends entirely on NAT64. The fact that those people don't show up in this study is interesting. I think I would flip your conclusion and say, the conclusion is that the RIPE probes are missing some really important, huge chunks of the network space, and are really going to give us some misleading results if we rely on them for anything that's essentially location related. I think it's really interesting to think about how we could get to that information. The first thing that comes to mind for me is thinking about how we could craft packets that won't pass correctly through NAT64, since NAT gateways are essentially ossifying, pretty restrictive. It might be possible to come up with some IP packets that will work on end-to-end connections but fail on NAT64, and that would allow you to run this kind of tests essentially over the web with arbitrary clients, arbitrary web browser clients.
Thanks, Ben. Please keep it moving quick. We're 1 minute over all the rest of the time for questions and answers today, and we've got 3 more talks coming up. So go ahead, Lorenzo.
Yeah, Lorenzo Colletti. I think the reason you won't find a lot of DNS64 in public resolvers is that the configuration of the DNS64 must be tightly coupled to the configuration of the network. You can only use DNS64 in the resolver that is in a network that is known to use NAT64, because the network and the resolver have to agree on the prefix to use. And so that's why you probably won't see a lot of this in public resolvers. A second Ben Schwartz comment, I mean, I think the issue is you don't have a lot of RIPE Atlas probes in, let's say, mobile network environments that's where NAT64 is primarily deployed. So that doesn't mean your study is not valid, of course. It just means that, you found what you found by looking in a place that is biased like all places. But I think the issue around like DNS64 is that sort of, in public resolvers, you wouldn't expect to find it. So that's something that we should keep in mind.
Robert Kustecki, Lorenzo stole my talk, but basically I would love to have Atlas probes in every network, but that's just, not reasonable. It's not going to happen. In particular, we are not really present in mobile networks where, as the previous commenter said, you might observe this behavior more often. So I would caution extrapolating the results from the presence of RIPE Atlas to the whole internet. The system was not designed to do that, and I don't think it can.
And probably you should have said that you're working for RIPE NCC on RIPE Atlas.
I work for RIPE NCC. I'm somewhat involved in RIPE Atlas.
All right, thanks, Robert. Thanks so much, Amanda. And if you have other things, you can put them in the public chat, or of course, contact Amanda directly. All right, we got Phil up next.
Hi, thanks. Phil Roberts.
Phil, we've got you 15 minutes.
Great, thanks. I'm Phil Roberts from the Global Cyber Alliance, and I'm going to talk about our interest in expanding honeypots to attract IPv6 attacks. And I'm not doing something correct with the advancing the slides. Oh, there we go.
Just passed it to you. You should have it now.
Excellent. Great. All right. So at GCA is a global cyber alliance. We're not-for-profit, US, UK, and Europe, and our goal is to help deliver a secure and trustworthy internet. We've been operating a honey farm for, I think, 6 years, certainly over 4 years. And our honey farm is a collection of 200 open source sensors that collect data of attacks directed towards IoT devices. When an attack comes in, we record everything that happens. We record every telnet and SSH attack. We record IP addresses, ports, embedded URLs, scripts, etc. We've been using this open source technology, but we're rolling out our own honeypot technology that allows us to do a few different things, one of which is attract attacks or detect attacks that come in over HTTP and HTTPS. We've recorded about 200 million unique attackers over the history of the project. Our daily attacks, the recording of attacks, detect attacks from 3,000 different ASNs each day. And we've recorded several billion attacks so far. We're doing two things with this. One is we're all about building collaboration, and we're working to build collaboration to clean up unwanted traffic originating from networks. So we partner with network operators, share data about attacks that we see coming from their network, and work with them to clean those up. The second thing we do is just research, and we partner with research institutions who want to look at our data. So if you're a researcher who's interested in this kind of data, please contact us. We've had a few public publications already. There's a link to one there from the Max Planck Institute. And there are others that are in the pipeline. So if you're interested in doing work in this space, please contact us. We like to build those collaborations. One of the things that we would like to do, though, is to extend this to detect attacks over IPv6. Everything we do is v4 only. And so we started investigating what it would take to do this. And we published a paper, and this is a summary of that. And I'd like to thank Microsoft for supporting this research. So how do our honeypots work? Well, essentially, they imitate an IoT device accessible on the public internet. And I say an IoT device because it's really a Linux device. And a lot of the attacks we see nowadays are attacks that are looking for a fairly high-powered Linux server. We see things in the scripts that try to detect the capability of the device and then deploy different things if it thinks it is a more high-powered device. We require everybody to log in. That's how we tell when it's an attack, but we accept almost any login credentials. That's how we allow them to make their attack. We record everything they do, but we don't allow attacks to be launched. Most of what we detect is malware distribution. And one of the interesting aspects is we don't really make any effort to be found. We rely on malware distributors scanning or using lists of previously scanned devices. And our sensors are distributed around the globe. I think we're in 60 different economies and all kinds of different networks. So where we want to go, we want to be looking at attacks happening over IPv6. IPv6 usage, as you all know, is trending upwards. IPv4 deployment is still pervasive. At some point, IPv6 only networks will emerge. And there are reports of some tidbits of malicious activity seen over IPv6 now. I don't think we're terribly well instrumented to detect a lot of that. So we're thinking that maybe more instrumentation would see more. And it would certainly be good to be ahead of the curve in detecting malicious activity directed towards IPv6, so we can know something about what it looks like and build preventative measures. And we would like to collaborate with others with similar interests and concerns. So how honeypots attract attention in the v4 world? Just by existing, really. Honeypots want to be found and attacked. We get scanned lots every day. We know that some of these are coming from security organizations. We know that some of these are coming from known botnets. There are new ones that appear. And typically we're scanned over 100 times daily. sometimes by people we know and sometimes by, and most times by not. But it's easy, as you know, to scan the entire v4 internet fairly efficiently. So this model kind of breaks down when you move to the v6 world, right? As you all know, it's the v6 space just can't be exhaustively scanned. Even just the interface ID space cannot be exhaustively scanned. So it's very difficult to find devices just by doing, the kind of scanning that goes on in the v4 world today. So this is a known problem. Researchers have been working on this. There are people who have legitimate reasons for wanting to measure the v6 internet, and so they want to know about devices that are attached to it, and they are developing techniques to do so. But how do you get your device found? Well, I think the first thing to do is to ignore IETF's very good recommendations about privacy and security. If you follow those recommendations, they're recommendations not only to prevent scanning, but to prevent activity correlation, location tracking, exploitation. If you follow that advice, your device is not going to be easy to find as long as it's not a well-known public device at a well-known public address. So people have been researching and saying, well, how are we going to find these things? How can these things be found? And a lot of the research has shown that it's often too easy to find devices in your public resources. Somebody will configure a server that has an entry in the DNS. And, if you look around the address of that device that's provided, the public address, if you search around it, you'll find other devices that aren't public that have just been configured, because that address is close to the one that we just configured. And so these things have been documented. People in doing this research have also observed that there are hosts numbered with just the prefix and the rightmost maybe 16 bits. So, there's some ability to scan in that kind of space. People have also noticed that certain things that would prevent detection and scanning aren't implemented in v6 or aren't enabled in v6 or aren't turned on in v6 that are turned on in v4. Of course, Honeypot would not want these protections, but it is something that's been observed by researchers. So mimicking these observed
Phil, we lost you in the room, or I hope we only lost Phil.
Yeah, I lost him remote as well.
Okay, yeah.
Okay. Yeah, just wait a few seconds, but I think we can switch to the next topic.
Or Leslie, are you able to?
Hi, Leslie Daigle. I can probably pick it up if he doesn't come back, but he's got a pretty craptastic home network. He should be back in a second. We're really kind of hoping for some feedback. So
yeah, if anyone has a question or comment, you can do that now.
Are you able to talk to the slides, Leslie?
I'll talk to the slides, and
You
we'll
can
hope
come
that he
here
does
as
in
well
fact
if you
come
want.
back. If Dave, you have control of the slides again.
I can share them again. I think we were about, where were we? 8?
Yes.
Yeah, I have control of them now. You want this?
No, I think. Hang on.
I think he was here.
Okay, so yes, I think we're ready to go on to the next slide for now. Yeah, we're not doing original research in this, and Phil made use of some prior research, which is very worthwhile to go through. Next slide, please. Yeah, so here's the key findings. There is a hit list of potential targets in IPv6, which is useful for establishing, to the extent you can, establishing a honey farm in IPv6 world, because it is where attackers might look. Phil mentioned that the compute possibility of scanning IPv6 is well, it's not really feasible these days. So not surprisingly, we aren't seeing a whole lot of IPv6 scans. There are some security companies that are attempting it, Go security companies. But then it seems like there are more tests that are looking at probing networks to see if there are vulnerable hosts, which is the kind of attackers potentially the kind of attackers we were looking for. So scanning is not really a viable methodology. Okay, next slide, please. From our own research, we struggled a little bit because apparently we live in lovely remote places that don't have IPv6 internet available. So we were a little bit struggling for test sites. But the thing that we noted was, in spite of whatever advice there is in IETF assignment and general assignment practices, these whatever size of assignment you had, it was typically not changed over 9 months of work. So there are clearly some implications in terms of how IPv6 addresses get assigned in terms of whether you're going to be visible and subject to attack. All right, I'm just going to go to the next slide, please. So building the honeypot is easy, deploying is a little harder, not only just because finding somewhere to deploy it with reliable v6 connectivity, but also the thing that we've been leading up to, which is it's very hard to get found, which is a basic tenet of having a honey farm. Yes, next slide, please. Yeah, some good advice in terms of what to do in terms of deploying an IPv6 honeypot. Yeah, next slide, please. And at this point, I would really love to hear from people, comments or questions. Suggestions for further work that we should do in terms of exploring the space of IPv6 honeypots. Y'all wish IPv6 would go away.
So as somebody that analyzes honeypot research, this is Wes Hardiker, USC ISI. Thank you for even trying to do this, because it's simply not easy to get out there. I certainly would love to compare, what you see difference-wise between attack space and either one, because hopefully more sophisticated. We'll definitely be contacting you guys for at least data. So.
Okay, in the interest of time, thanks, Lizzie, for picking that up. I think we should switch to Wes's presentation. We're already past the end of the time. Ben, do you have something? Let's see, we got somebody in the queue. We got in there. Yeah, we got 25 minutes of presentation in 23 minutes. So let's switch to Wes.
I'll try. So I'm Wes Hardiker, as I just said, USC ISI. I'm since this is DNS data in the talk, I'm also a member of the ICANN board. I'm not speaking for the ICANN board. Next slide, and when you give me control, I'll do that too. There we go.
I just gave it to you.
Yep. So as a network operator, and there are a few of us that are both network operators and protocol engineers, we get plagued with graphs like this. This is a live graph and we get all these random bumps, and it's like, well, what are they? And sometimes they're really important to figure out, especially when you're about to be under attack. Sometimes they're just regular monitoring spikes, little tiny ones. You can figure those out pretty easily, but the really long flat ones that are really low and narrow, it's much harder to figure out. So I went about thinking about this. Well, how can we do more intelligent analysis? How can we figure out what actually is in those bumps? And the way I finally decided to think about it is what's normal versus what has been added to it by the bump, right? And this is very similar to when you go see a doctor. You go see your doctor and you say, hey, I stubbed my toe. And he says, take your shoes off. And you take off your right shoe and you show him the toe and he's like, no, take off both shoes. And he does that because he doesn't know what your toe normally looks like. He doesn't see you every day, right? He wants to do bilateral differential comparison. So this is what doctors do. And I'm going to argue throughout this talk that this is what we should be doing in the network world as well. And so continuing my analogy, in a DDoS attack, you know what's going on. Anybody watching TCP dump output or just live traffic in Wireshark or whatever it is, It's very obvious, right? Something has shifted drastically. You know that the green is now overwhelming you in this simple pie chart example, and everybody would know what it was. The little tiny bumps are much, much harder. So here are two graphs. There's actually a difference between them. Can you see them from where you are? I'm betting no. So one way to figure out this, right, is you sort of take one, you decrease the alpha level if we're doing it graphically, and you overlap them. And now if you look at how they overlap, you can sort of see maybe kind of where there's a difference. So if we zoom in, you'll see that there's actually two spots. There's one on the bottom, which is fairly obvious, but there's actually a little bit of difference at the top, just where the percentages have shifted, right? And this is contrived, but the important thing is when you do this subtraction, when you take the normal out of the abnormal, you're left with just the abnormal, right? You take it out of the bump, you're only left with the abnormal. So it's a very specific space. So one huge caveat is people kind of want to, take this sort of idea and apply it to anything where it goes up. And that doesn't work. It's got to be a change where there's a change in the type of traffic that you've been seeing. It doesn't matter whether these are DNS traffic graphs, but it doesn't matter whether it's web traffic or anything else. It doesn't work for the diurnal patterns that you get of, well, everybody woke up and now there's just more web traffic and it's really not that different, right? It matters where somebody out on the internet is suddenly shifted something in a fairly major way, whether it's a configuration change or a traffic anomaly because of an attack or whatever. So a little bit of terminology. The way I ended up defining this in the tool I developed is, there's a notion of left and a notion of right. You want to compare a left thing against a right thing, where left is normally, in my example, is going to be normal traffic, and right is going to be the anomaly. It can be anything. It can be two time slices. It can be two files. It can be two anything. But left and right is just traffic-wise terminology. So I created a tool called Traffic Taffy that helps do this analysis for you. And it actually does deep packet inspection. You give it a baseline saying, this is what my normal traffic looks like. Take this slice as normal. Here's a slice where I don't understand what's in it. Show me what's changed. And it does this by looking at each value and counting, enumerating every value seen in every protocol field. And it has sort of levels, so it's more intense to get the deep packet inspection, but the deeper you go, the better results you get. And so there's a couple of tools. There's Dissect that just breaks things down for you in a single slice. There's a Compare tool that actually will do the analysis for you of trying to show you what has changed. And then you can graph anything as well. And it's very easy to install. It's in a Python module called Traffic Taffy. It is sort of beta. It used to be alpha. It's sort of beta. So let's go back to a real world example. So this is another traffic of DNS graph. It'll do anything. This example is going to be DNS based. So these were 3 5 time increases, and it'll do easier things than this. At one Anycast site, for those that don't know, I'm a root server operator that runs the USC-ISI root server. And so I kind of wanted to see what's in this. Can we determine what the right thing is without knowing, what to actually go look for? So again, there's a left and a right. The Taffy Compare tool basically takes a couple of PCAP files and looks what's inside of them, tries to figure out what's normal, does a count, figures out where's the shift, where's the massive increase or decrease into the next swath, and it outputs console information, which I have an example of at the bottom. And so this is sort of the output of what are in those two tools, where it gives a colorized console output. It's going to be a little bit hard to read, apologies for that, but here's the breakdown. So I didn't pick what this tool reported. It did this based on sudden increases or decreases. You can see that over DNS over UDP over IPv6, there was suddenly a whole bunch of name queries for number : number, right? Anybody that has ever used Docker knows this is now, leaked queries where somebody put port mapping in the wrong field, right? And we got a ton of them, so clearly it was a configuration mistake, not likely an attack. They were all looking for A records, so that line came up. We returned more NX domains because this is actually including our response traffic. And the truncation bit in DNS increased, saying you need to come back over TCP. You sent us way too many requests. We don't think you're a real UDP client. And it all went to our older IPv6 address to make it worse, right? This is actually not our current one. It went to our older, no longer technically in production IPv6 address. The important thing here is this screenshot is a full screenshot of what it showed me. I'm not clipping it out with other stuff. It actually figured out each of these things to show me. It's dropping anything else in the DNS or other packets that is unrelated to what it found. I will warn you, it's really easy to chew all of your CPU. I did make it parallel processing, so it'll take some large PCAP files and use everything available. I've run out of memory before. That was the only time I made a big mistake. So I am looking for feedback on the website there, which is traffic-taffig, and it's readthedocs.io or traffic-taffig.github.io. There's some longer video presentations. There's some that are half an hour long that give like 4 or 5 examples of how it can be used and what can be found, including some lower level bumps. I've given the talk at DNSORG and other things as well. It's easy to install, and great thanks to the Comcast Innovation Fund, which actually sponsored this work. I appreciate their help. Any thoughts? And again, if you have any traffic that you actually want me to help you analyze, I'm always looking for more things. I'm actually now bored when my graphs look flat because I actually want interesting things now. Any thoughts? Any questions?
We have Laurent in the queue.
Yeah,
Go ahead,
hi.
Laurent.
Yeah, hello. Thanks. Looks very nice. Just a question. Do you need any, engineer or subject matter expert to tag actually what looks like an anomaly?
You have to give it a time slice where the anomaly is and a normal slice where the traffic was normal, and then it tries to do everything else for you. There's actually a couple of different algorithms. I don't have time to go into that.
Okay. Do you put any kind of rules, or what the tool needs to look to? It's more like based on statistics.
Correct. You can give it TCP filters if you want to narrow it down, but no, it does full packet all the way, whatever it can find.
Yeah. It looks very interesting. Thanks.
Yep. Thank you.
Yeah, thanks a lot. Hopefully we will get a lot of talks using this tool in future.
Yeah, that looks cool. Thanks, Wes. All right, so we have Jason up next. Let me get his slides up. And Jason, I'm going to give the control to you. You should have it now. And it looks like you got 14 minutes.
Okay, cool. We'll see what we can do. I know everyone wants to get out on time, so I'll do my best. So my name is Jason Gertzen from Sandbox AQ. I'm going to be talking about a collaboration that we did with DSEC, looking at post-quantum DNSSEC. So a little bit of context before we dive in. This is actually a follow-up to some work that the DSEC folks did, where they evaluated local-only DNSSEC with the Falcon algorithm. But we want to look at how these PQC algorithms behave in the wild, right? If you can just run on your local machine and it works, that's not a fair representation. So we want to see if there's any funniness in the network. So we wanted to deploy some test zones and get as many measurements across the internet as possible to see how things go. And we wanted to evaluate across a couple of different scenarios. So we wanted to look at what would happen if you rolled a KSK and ZSK, as well as just a CSK. And then we also wanted to look at what would happen if a name existed versus it didn't exist, and then if it didn't exist between the two different versions of NSEC and NSEC3. And then also we wanted to look at what happens when a client does the request by UDP or TCP to the resolver, and then if the DO bit was set. So if you've been in the PQ space, specifically the PQ DNSSEC space, you've probably seen this table, but if you haven't, that's fine. The big takeaway is at the very bottom, you can see the classical algorithms, and they all have very nice signature and public key sizes. But then if you start looking at the PQC side of things, such as Falcon or Dilithium or Sphinx, it kind of becomes a horror show. They get quite a bit larger, in some cases 2 orders of magnitude or more larger. So that could cause some issues in the DNSSEC setting. So we look at a bunch of these, including a stateful hash-based signature algorithm called XMSS. Specifically, we looked at Falcon 512, Dilithium 2, and Sphinx Plus 128S. And we used the amazing test network RIPE Atlas with about 10,000 probes. And we actually performed about 4.5 million queries. That's a typo. And then we stored things such as the return code, correctness, So were we expecting this return code? Did we actually receive what makes sense? Was the AD bits set? And then also the response time, which we don't report in this because it wasn't particularly interesting. We did do some filtering though. So we decided that if you give the incorrect results for RSA SHA-256, then you probably are giving the incorrect result for pretty much everything related to DNSSEC, so it doesn't really inform us on PQC, so we filtered those out. We also filtered out, due to some a limitation with the right batlist TCP implementation, we filtered out all private, all of resolvers in private IP ranges, and then we also filter out timeouts and network errors. So if you were to do a dig to one of our zones using, in this case, Google's resolver, you'll get something like this. And the big takeaway is the AD bit is not set, and that's what you would want because Google doesn't know how to resolve, in this case, dilithium 2. So it just passes it forward to us. So getting into some numbers here. If you look at the classical algorithms, they more or less behave 100%. You get no errors near or close to 100%. And then as you look at the PQC algorithms, and this is for bind 9, you can start seeing more and more failures. For a little bit more context, which I probably should have done first, the top row is using UDP to contact the resolver. The bottom row is using TCP. The left column, the DO bit is set, and the right column, the DO bit is, the right column, the DO bit is set, the left column is not set. The other thing to take away is when the DO bit is set, we sometimes see higher rates of failure. When we look at the power DNS settings, so this is using 1 key instead of 2, things improve because we're transmitting less bytes. We see about a 15% improvement in general. And then Falcon, which is the smallest PQC signatures and keys, approaches less than 2% error rate. So that's quite promising. If we look for non-existence, it's more or less kind of the same story. As you start using signature schemes with larger signatures and larger keys, you start seeing more and more failures. And we get more and more serve fails between 38 and 44%, depending on what we're looking at. You'll notice there's a lot more algorithms on the side there. That's because we're looking at NSEC and NSEC 3. The NSEC 3 algorithms are the ones that are postfixed with a 3 at the end. So if you look at the slides later, NSEC 3 is the one with the 3, the trailing 3. If we look at Power DNS again, we actually use different NSEC 3 configuration here. In Bind, we use the conventional one. In Power DNS, we use narrow. And in fact, we start seeing some errors for XMSS because the actual response size exceeded 64K. So the entire message wouldn't arrive. So now correct response. This is kind of more of a high level look at what we've already talked about. So it looks at, did we get the return code we were expecting, as well as Sandy checked if there are A records in the response, for example. And it's more or less the same sort of story. You'll see that there's up to a 70% correctness, but it improves by about 10% once you start using TCP. And when you have the DO bit set, it falls apart when you're using UDP. And then when we go to the single key, maybe, when we go to the single key scenario, we see a 15% success rate improvement. So that's nice. Okay, so this is looking at the AD bits. So for those that aren't familiar with DNSSEC, what will happen is the resolver, if it's able to validate, it will then set the AD bit to mark that it successfully validated the response and then pass it to the client. A good third of the resolvers would set the AD bit for the classical algorithms, which is consistent with what we've seen and other studies we've done in the past. But interestingly enough, 8.5% set the AD bit for Falcon, which is quite interesting because there's no way for Falcon to be validated, or unless they read our minds, I guess. So that's just kind of an interesting artifact. Keep losing connection. There we go.
Okay.
And no difference for the CSK situation. And this is more or less what I've said, and in the interest of time, I want to move on to one or two more things. But more or less, the really big takeaway is if we use large signatures, you see large failures. And unfortunately, with PQC, it's kind of hard to get away or get around the large signature situation. So really quick, we did some benchmarking using the PDNS algorithm testing tool just to see how things compare. The top bars are your classical, and your bottom are the PQC and hash-based signature examples. And you can see that Falcon and Dilithium, in terms of their sign and keygen and verify operations, are pretty performant. XMSS and XMSS MT keygen is quite depressing, and Sphinx signing is quite depressing. So that will limit, even if we figured out the sizes, that would limit adoption for sure. Now, just to make sure that we're actually successfully verifying things, we actually set up some public resolvers as well that you can dig. So in this example, we are querying a zone that's signed with dilithium 2 and served with power DNS using a bind9 based resolver. And as you can see in the green there, the AD bit gets set, so we successfully validated. And Peter spent a bunch of work making a nice web app for you to go and try this. This will let you select what kind of records you want. It'll let you set algorithm, the vendors for both resolver and the name server, and if you want a non-existent name, as well as if you want to use NSEC3. And our next work that we want to do a follow-up on is we want to see how Merkle trees affect things. We want to see if we can use this as a compression mechanism to handle these large PQC signatures. So the idea is your signatures will become authenticating paths in a Merkle tree, and then your ZSK DNS key just becomes the root hash of the Merkle tree that you've constructed. And then the KSK is some secure algorithm you want to use, whether it's dilithium or Falcon or whatever. Just kind of to give context of what kind of compression you can get, we had a dummy zone file that would generate 10,000 signatures. Using P256, you would get it'd be about 2 megabytes. If we look at dilithium, just pure dilithium, it's 38.8 megabytes, so that's quite horrific. But if you use a Merkle tree to compress it, you can get almost 4 times better to 10 megabytes. And Falcon, it's a bit less of a win because the authenticating path was starting to approach the size of a Falcon signature, but you still saw some wins there. Based on some previous work that we submitted to CTRSA, we think we can actually shrink the Merkle tree authenticating path significantly. But we're going to have more to talk about on that in the next coming months, hopefully. So thank you very much, and happy to answer any questions you may have.
Hi, Ben Schwartz. I think it's really cool to see a running demo of post-quantum in DNSSEC. That's cool. For the public resolvers, what algorithm IDs were you using? Because of course they don't exist.
Great question. So we wanted to use IDs that looked normal instead of the private algorithm identifiers, so we wouldn't get any preferential treatment or weird treatment. So we used the IDs 17 through 22.
Okay, thanks. So correct me if I'm wrong. It seems to me that under the usual assumptions, the only thing that matters here is the size of these signatures. That is because the receiving resolvers can't do anything with them. So they're just opaque bytes as far as everything else in the chain is concerned.
Yeah, more or less. The size is the primary concern and would be why we're seeing failures.
Yeah. So for as a DNS standards developer, the thing that would be really helpful to me here is to have forget about the algorithms. Show me the curve of success rate versus signature size or key size, right? Because that curve is the trade-off space that we're faced with.
Right.
And the shape of that curve is really interesting and something that's super important to measure.
One thing worth mentioning, and I can maybe show you afterwards, but for Falcon, it stays under that magical MTU number for a lot of its messages of about 1,200 bytes or something like that. And then all the others exceed that number. And Falcon's the one that gets the closest to having a non-zero error rates. When we were using TCP in Falcon, it would approach 2% failure rate instead of with some of the signing algorithms that were quite large would approach like a 50% or something. So it's quite substantial, but that's a really good point. Thank you.
Yeah, thanks, Ben. That seems like a good idea for a way to present the results. And Jason, thanks so much for taking us to the end of this nice session. I appreciate it. Thanks to Miria for organizing the lion's share of the work. And I think we can close out the session. And that'll be, I hope you guys have enjoy the rest of the week if you're there, and even if you're not.
Yeah, also thanks to the note takers, Eric and Eric, and thanks, Dave. See you next time.
Bye-bye.